In this video, we will discuss about shortest distance after road addition queries 1. You are given an integer n and a 2D integer array queries. There are n cities numbered from 0 to n minus 1. Initially, there is a unidirectional road from city I to city I plus 1. Queries of I represents the addition of a new unidirectional road from city U to city V. After each query, you need to find the length of the shortest path from city 0 to city n minus 1. Return an array answer where for each I in the range 0 to query's length minus 1, answer of I is the length of shortest path from city 0 to city n minus 1 after processing the first I plus 1 queries. So what they are saying is that in the input, we are given an integer n which denotes the number of cities, and we are given a 2D vector which represents the queries. So initially what they are saying is that there are n cities which are numbered from 0 to n minus 1, that is 0 to 4. Now initially there is a unidirectional road between city I and city I plus 1. So basically there is a road between 0 and 1 which is starting from 0 and going towards 1. Then from 1 to 2, 2 to 3 and 3 to 4. So initially this is what it looks like. Now what we need to do is that we need to process each of these queries. In each of these queries, what we need to do is that if we take this first query, then it is 2, 4. So this means that there is a new road that is added from node 2 to node 4. That is from here till here. After adding this edge or this road into this particular graph, you need to identify that what is the shortest path between the node 0 and the last node, which is node 4, n minus 1, right? So for the next query, we need to do the same thing, but for this, the edge that we added for this query will be present. We need not to remove them. So when we will come at this, there will be an edge from 2 to 4, and we need to add an edge from 0 to 2, so our graph will look like this. Right? So at each query, we need to find out the shortest path, write it in some vector and return it as our answer, right? So since we are talking about finding the shortest path, and this is nothing but a graph, right? We have some nodes and we have edges connecting that node, right? We have directed edges connecting the nodes. So can we say that we can apply breadth first search here or BFS here for finding out the shortest path? So when we apply BFS for finding out the shortest path, what do we do? So see, if we look at the first query, so it is giving us an edge from 2 to 4. So if we draw that edge, so we'll get 2 to 4, right? Now, if we apply breadth first search over this graph, what happens? So breadth first search works at levels, right? So basically it processes each level one by one, right? So we maintain a queue for that. So in the queue, firstly, we will be having the node 0, right? We will be having the node 0, and then after node 0, whatever will be the neighbors of this node, that we push into the queue, right? So if you see, 0 is connected to 1. So after 0 in the queue, we push 1, right? Then after 1, it is being connected to 2. So after 1 in our queue, 2 will be present, right? Then we see the neighboring nodes of 2. So for 2, we are having 2 neighboring nodes. One is 4 and one is 3, right? So node 3 and 4 will be present in the queue, right? And then so on. So this is what happens in the BFS, right? Now here, since you are going level by level, you know this is the level 0, this is level 1, this is level 2, this is level 3, right? So whenever at any level you encounter the final node present, meaning the n minus 1th node, if you encounter at any point in the queue, which you will encounter here, then at that point, whatever is the level, that is denoting you the shortest path, right? See, if we see in the graph, what was the shortest path? 0 to 1, 1 to 2 and 2 to 4. It was total 3, right? That is what we will get from here also. So through applying BFS, we can find the shortest path, right? So how are you applying BFS? So first you will have to maintain an adjacency list of the graph, right? So adjacency list is nothing but it denotes that for each node, what are its neighboring nodes, right? So if you will try to draw the adjacency list of this particular graph, what you will get? So for node 0, the neighboring node is 1. For node 1, the neighboring node is 2. For node 2, the neighboring nodes are 3 and 4. For node 3, the neighboring node is 4. and for node 4 there is no neighboring node, right? So this is how the adjacency list of the graph looks like, right? Now through this adjacency list, now since you need to identify the shortest path from node 0 to node n minus 1, so the starting node is always fixed, so you can push node 0 into the queue, right? So node 0 will be present initially, and then from the adjacency list you can identify what all neighboring nodes we have for the current node. You can push them into the queue, right? And for each level you will have to maintain a variable level also for counting this, right? And whenever your current node becomes 4 or node n minus 1, then whatever is the number of levels, that is your answer for that particular query, right? So when we will code, then you will be able to understand better how are we applying breadth first search here. So see, through BFS we are able to identify the shortest path, but when we move on to the next query, there is one more edge which is being added to our graph, which is 0 to 2. That means we will have to update our adjacency list, right? So for node 0, now in the adjacency list we will have 1 as well as 2, right? So now since our graph is updated, our shortest path will also be updated, right? If you closely look, now the shortest path will be 1 2, only 2, right? So then how are we going to do? So given the constraints in the questions, given the maximum number of nodes as 500 and the length of queries also as 500, can't we apply brute force here? Brute force meaning for each query, can't we go and update our adjacency list, and then taking this adjacency list and our source node as 0 and destination node as n minus 1, can't we keep on applying BFS and find out our answer? It is going to work, right? So what we will do is, we will take one query, we will update adjacency list, we will apply BFS, find the shortest path, that will be answer to this particular query. We will take next query, again we will update the adjacency list, apply BFS, find the shortest path, update the resultant array, and so on, right? So this is what we are going to do. So let's quickly code it out to understand better. So first of all, we will create a vector which will store our result, right? Now we need to create an adjacency list for our graph, right? So that will be a vector of vector and it will store an integer, right? Let's name it adj. So this denotes this is the adjacency list. What will be its size? Equal to the number of nodes, right? And initially we will keep the neighboring nodes as 0, right? Basically the length as 0, right? Now we need to update the adjacency list. So now initially it is given to us that there is a road for each city I to I plus 1, right? So we will run a for loop of I starting from 0, I less than n, I plus plus, and then inside this what we will do? In the adjacency list, at the index I, we will push back I plus 1, right? So these are the initial roads or the edges that are given to us, right? Then we need to process each of the queries, right? So we will iterate inside the queries. So for auto road in queries, right? Now inside this, we will get a node U from which the edge or the road is starting. So this will be 0th index of road, and we will get a node V which will be the first index of road. So basically we have a road starting from U to V, right? So in the adjacency list at the index U, we will push back V, right? We can write it in one line also, but to make the code a little simple and easy to understand, we can write it like this also. And then we need to update our answer, right? So in our result, we will push back. What we will push back? So we will apply breadth first search, right? For this instance of our adjacency list, right? So we will create a helper function named BFS, right? It will return us the shortest path. And what all are we going to pass in it? So we can pass the number of nodes and we can pass our adjacency list, right? And at the end, you can return your answer or the resultant vector, right? So let's create the helper function now. So this will return us the shortest path, which will be an integer. We will name it BFS, right? It will receive the total number of nodes and the adjacency list, right? So this is our adjacency list. Now inside this, see, now when we are processing our queries, it might be possible that at some point we have added such a edge in our graph that our graph has become cyclic, right? So in that case, we do not have to end up in a cycle, right? So we will also have to maintain a visited array or a visited vector to mark a particular node which has already been visited, right? So that we do not process it again, right? So what we will do is we will take one more vector which will be of type bool, and we will name it as visited. It will be equals to the number of nodes, and initially all of them will be false because none of them is visited, right? Next, we need a queue for performing breadth first search. It will store an integer. We will name it q, right? Now, initially, we will put our source node, which is the node 0 inside our queue. So, q dot push 0, and then we need to mark it as visited also, right? So, in visited, at 0th index, we will make it as true, right? And we need a variable for counting the levels also, for counting the shortest path, right? So let's name it levels. Initially it will be 0, right? Now we will apply breadth first search. So while our queue is not empty, right? While our queue is not empty, what do? We take the size of the queue, right? So in size equals to queue dot size, and then we run a loop equal to the size, right? So we will run a for loop of I starting from 0, I less than size, I plus plus. Now inside this, what do? We take the front node from the queue, right? So int cur equals to queue dot front, and we pop it from our queue, right? So now, since we have taken a node from the queue, which is stored in cur, so cur basically is denoting the current node. Now we should check whether this current node is the final destination node or not. That is, if it is equals to n minus 1 or not, right? So if cur is equals to n minus 1, then in that case we have reached the destination node and we need to return the shortest path now, right? And shortest path is being stored in the variable levels. So here we will return levels, right? Otherwise, what we need to do is we need to process all the neighbors of this current node from the adjacency list. And if they are not already visited, then we need to push them inside our queue, right? So we will run a for loop in the adjacency list for the current node. So for auto node in adjacency list of current node, right? Now we need to check whether this particular node is already visited or not. So if this node is already visited, then we will just continue. We won't do anything, right? Otherwise, we will push it inside our queue, and in the visited vector, we will mark it as visited, right? Now, after you are done with this particular level, so this loop will run for each of the levels, right? So after we are done with this, we will increment our levels by 1, right? So this was the only code that we needed to do. So let me just decrease the font size. Yeah. So this is our breadth first search that we have applied. And now here at the end, you can return anything because the destination node will always be present in our graph and it will always be reachable. So in each of the case, your answer will be returned from here. But just to get rid of the compilation errors, we can return anything from here. So let's return -1, right? So this is how our code is looking. So let's run it now. So our test cases are accepted. Let's submit this. So it got accepted. Thank you so much for watching. Please like the video and subscribe our channel.